Hello students, this is Professor Chalai, and in this video we're going to look at Lewis structures for molecular compounds. As always, you can follow along with our Chapter 7 workbook. And by the end of this video, you should be able to describe bonding and lone pairs, so bonding pairs and lone pairs. And you should also be able to draw the Lewis structures depicting covalent bonding, different kinds of covalent bonding. So earlier when we talked about bonding, I mentioned briefly that we talk about sharing a pair of electrons for covalent bonding. And I talked about how a pair of electrons is important, and we're going to talk about it later. Now is later. So a bonding pair simply refers to a pair of electrons that are shared between two atoms in a chemical bond, right? Electrons always like to be paired. Well, not always, but most times electrons would rather be paired than unpaired. We talked about the reason why electrons are paired in the first place is because they have different values for ms, either plus half or minus a half. And typically electrons like to be paired up with another electron of the opposite spin. So if one electron has a positive half ms value, the other one will have a negative ms value, just because that's what they like to do. And so whenever two electrons are shared between two different atoms, we'll call that a bonding pair, whereas a lone pair is just a pair of electrons that is not involved in chemical bonding. Involved in chemical bonding. And when we draw our Lewis structures for these, we'll see what we mean. But if there's a pair of electrons that's involved in bonding, that's a bonding pair. If there's a pair of electrons that are not involved in bonding, that's a lone pair. That's how we refer to them. Now, before we look at Lewis structures for bonding, let's talk about the octet and the duet rules. So for most elements that we're going to be interested in this course, they sort of fall, if you look at a periodic table, they mostly fall sort of in the top half or the top part of the periodic table. Let's say that bit of the periodic table, because that's the most, these are the most abundant elements in the universe as it happens. And for most of these, if we ignore the first row for now, most of these will have an S subshell and a P subshell, right? An S subshell and a P subshell. Even in this category, there's an S subshell there and a P subshell there that makes up the valence orbitals. So with an S subshell, we know it can fit 2 electrons. A P subshell, we know can fit 6 electrons. So in their valence orbitals, the most number of electrons that they could fit is 8 electrons, right? For things like hydrogen and helium, let me just use a different color. For things like hydrogen and helium, they only have a 1s subshell, so they can only ever fit in their valence orbitals 2 electrons, right? So these guys can only fit 2 electrons, whereas pretty much everything else up to this row in the periodic table can fit, there we go, can fit at most 8 electrons in its valence orbitals. So when we're looking at Lewis structures, where are we? We're right here, right? We can fit at most 8 electrons in the valence orbitals, except if we're looking at hydrogen and helium, in which case we can only ever fit 2 electrons. And so that's what we mean by the octet and the duet rule. The octet rule is simply elements would want to have as many electrons as they can in their valence orbitals, such that they have a completely filled valence orbital. So for things like oxygen and carbon, that means they want to have 8 electrons, 8 valence electrons around them. And for things like hydrogen, they want to have 2 electrons around them. That's the duet rule, duet for 2. So whenever we're thinking about Lewis structures and whenever these atoms come together to form bonds, they want to have a completely filled valence orbital as much as possible. Okay, so what does that mean for bonding? Well, let's look at the case of water, right? We know that water is made up of two hydrogens and an oxygen. We know that this is the Lewis structure for an oxygen atom, right? It has two pairs of electrons, and then there's two unpaired electrons. And then for hydrogen, there's only one electron in hydrogen, so that means that it's not paired up. It's just one dot there for the one valence electron. There we go. Now, these atoms are not happy just like that, right? Because hydrogen wants 2 electrons in its valence orbital, and oxygen wants 8 electrons in its valence orbital. So here's where the sharing comes in. So hydrogen is kind of like, hey, I can lend you my 1 electron if you lend me your 1 electron. So those two are going to be shared between hydrogen and oxygen. And then on the other side, it's the same thing. Oxygen is going to be like, hey, I'm going to lend you this one one electron, sorry, that I have that's not paired up. And you're going to lend me this one. So if you think about it from the oxygen point of view, we'll have 1, 2, 3, 4, 5, and 6, because it's sharing that one from hydrogen, 7 and 8 electrons around it at any one point in time. So it's kind of happy. And then from the hydrogen perspective, right, hydrogen has this one, and then this one it's sharing, so that's 2. So this hydrogen is happy. Similarly, this hydrogen has 1 and 2 that's sharing, so it's happy. And so by sharing these 2 electrons, let's use a different color so that we can see it. By sharing these 2 electrons, we can rewrite that as a single bond. Again, over here, they're sharing 2 electrons. They're sharing a pair of electrons. That becomes a bond. So what did we do? Well, instead of writing a dot here and a dot here that they're sharing, we erased it and draw it as a single bond between them. That's one bonding pair that we talked about above, right? Bonding pair. So in a bonding pair in a Lewis structure, we just represent as a line to show that bond. We ignore the dots. Similarly here, we draw a line to represent the bonding pair. We ignore the dots. So we have to remember that every line is a bonding pair of electrons, so it represents 2 electrons. So if we're trying to count the valence electrons in oxygen, there's going to be 1, 2 for the 2 dots, 3, 4 for those other dots, 5, 6 for this bonding pair, and then 7, 8 for this other bonding pair, because technically oxygen is sharing all of those, or oxygen thinks it has all of those, and so it has a completed octet, 8 electrons. This hydrogen is we only have the bond to deal with, which is already 2 electrons, so it has a complete duet, and this hydrogen also has a complete duet. And if you're wondering, we talked about how these lines represent the bonding pair. These dots that are left over, they're not involved in bonding, so they're the lone pair of electrons. Here's another lone pair of electrons. All right, so the idea of sharing these pairs of electrons then are responsible for what we call single, double, and triple bonds. So if you're sharing 1 pair of electrons, like we did up here, you have a single bond. If you share 2 pairs of electrons, you have a double bond. If you share 3 pairs of electrons, you have a triple bond. Let's talk about that in a little bit more. So again, we have 2 oxygen molecules, right? Or oxygen atoms, sorry, each with 2 pairs and 2 unpaired electrons. Each oxygen wants to have 8 electrons, so they're like, hey buddy, let's share these electrons and then these electrons between each other. So now we'll have the one on the left will have 1, 2, 3, 4, 5, 6, 7, 8 electrons. And similarly, if we do count the ones on the right, we'll have 1, 2, 3, 4. These two are shared 5, 6. These two are shared 7, 8. So both oxygens have 8 pairs of electrons, and so these 2 electrons are shared, so we draw that as a bond. These 2 electrons are shared, so we draw that as a bond, and so that's why we have 2 bonding pairs, and then each electron has 2 lone pairs. Each atom, sorry, has 2 lone pairs. So this tells us that when oxygen bonds to oxygen for the O2 molecule, there's actually a double bond between them, not a single bond. We can do the same idea with nitrogen. They'll share these 2, maybe these 2 and these 2, so that each will have 8 electrons, and so we have a triple bond. Let's count them though. 1, 2. Let's count the ones on the left. We have 1, 2, and then each line is 2 electrons. So 3, 4, 5, 6, 7, 8. And the same is true for the right. Remember, each line, each bond represents a pair of electrons. So that's 2 electrons. Okay, so here's some rules for drawing the Lewis structures of molecules in general. So here we talked about how we can go from just atoms to having bonds in between them. We have bonds by sharing electrons, right? Well, some rules in terms of drawing the Lewis structures of very large and complex molecules is we first draw a skeletal structure. A skeletal structure is just sort of show how the atoms are generally connected. Maybe for, something like this. This could be a skeletal structure. Just sort of draw how they're connected. And there's some rules to trying to figure out how to draw the skeletal structure. Typically, we put hydrogen atoms in a terminal position, meaning if we're drawing a chain, right, hydrogens will be at the end. They can't be in the middle. Because why? Hydrogen can only ever have a duet, which means that it can only ever have 2 electrons in its valence orbital. We know 2 electrons is the same as 1 bond, which means hydrogen can only ever form 1 bond. So if it's in the middle, well, it can never be in the middle because to be in the middle, you need to form more than 1 bond. So it can only ever be at the ends. So that's one of the rules. Another rule for drawing a skeletal structure is to put more electronegative atoms in the terminal positions as well. So if you have, let's say, carbon and oxygen to deal with, right? You put the oxygens in the end positions. That's just a general rule to start with. We're not going to draw something like this where we put the carbon in the end positions because that's not how it works. If you want to figure out which elements are more electronegative than which others, we have that table all the way up here. The higher the value, the more electronegative it is. And so here's carbon, here's oxygen. Oxygen is more electronegative, so typically we will put that at the ends. All right, so that's the first rule to drawing the skeletal structure. Once you have some sort of skeletal structure to work with, the second step is to count the number of valence electrons. So you count all the valence electrons for every atom. That's where a periodic table will come in useful, right? Because we could easily go across the row and try to figure out how many valence electrons it has. For example, let's look at phosphorus. We know it'll have 1, 2, 3, 4, 5 valence electrons. Okay. The third rule for drawing Lewis structures, and I'm going to do examples with all of these so they become clearer, is we distribute the electrons to give full octets or duets to as many atoms as possible, right? So now that we know how many electrons were there, we're just going to start distributing them to all of the atoms. And then finally, if any atom does not have a full octet or duet, we'll start to form single, double, or triple bonds so that they have a full octet or duet. I know this seems like a lot, but let's do some examples and we'll see what we end up with. Let's start with carbon dioxide. So first we start with the skeletal structure, and we talked about how oxygen is more electronegative than carbon, so oxygen must be at the ends. So we'll draw carbon with oxygen at the ends. That's our skeletal structure. Now let's look at valence electrons. Oxygen has 6 valence electrons, carbon has 4 valence electrons, and oxygen again has 6. So we have in total 16 valence electrons, right? But we already drew 2 bonds here in the skeletal structure. Each bond is 2 electrons, so we need to minus these 2 times 2, 4 electrons. So we have 12 electrons to assign. We have 12 electrons left over to assign. So let's start assigning these 12 electrons to these atoms using dots, right? Because we know that dots are the other how we draw electrons in Lewis structures. All right, so we have 12 to assign. Where do I put them? Well, there's no really good way to start like sharing out electrons. You can use any strategy you want. I know because oxygen are more electronegative that I'm probably going to start there and then see what I end up with. So I need to share out 12, and I'm going to start putting them in pairs. So there's 2, 4, 6. I can't add any more to oxygen because that's a full octet, right? 2, 4, 6, and then there's another 2 from the bond. That's 8. So I need to do 6 more, so let's add it to this oxygen. 2, 4, 6, and then the bond is another 2, that's 8. So those are all the 12 electrons that I had to share out. So my 2 oxygens are happy, right? They each have 8 valence, they each have a complete octet, but my carbon is not happy. My carbon has only 2 bonds to it, so that's 4 electrons. Carbon wants to have 8 electrons in its valence orbital. So how do I get 8? Well, I could share 2 electrons from this one, 2 electrons from that one, because why not? Oxygen has enough and it could share. So if I do that, then these 2 electrons, remember 2 electrons become a bonding pair, so that becomes a bond. And these other 2 electrons become another bond, and I end up with a situation like this. Now carbon has 1, 2, 3, 4 bonds, or 8 electrons, so it's a filled octet. Oxygen has 2 bonds, which is 4 electrons, and another 4 electrons from the dots. This oxygen, the same thing, so we're all happy. This is the Lewis structure for carbon dioxide. All right, with that, try to do the others on your own. I'm going to go over them one by one, but see if you can get them yourself. Okay, so let's look at NH3. If you haven't done so already, please pause the video and try it for yourself. So let's draw a skeletal structure, and we talked about how hydrogen should always be at the ends, the terminal positions. So let's put hydrogens at the terminal positions. There we go. Okay, let's count valence electrons. How many valence electrons are in nitrogen? Well, let's see. Go to our periodic table. Nitrogen will have 1, 2, 3, 4, 5 valence electrons because it's right there. So we'll have 5 valence electrons from the nitrogen and 1 each from the oxygen. So there's 3 from the hydrogen, sorry. So there's 8 valence electrons, but 2, 4, 6 of them are already taken up in bonds, right? There are 3 bonds, each of them are 2 electrons, so we need to minus those 6 electrons. That means we only have 2 electrons left to distribute. And now we're going to start with, we can't put them on the hydrogens because hydrogens can only fit 2 electrons and they already have those 2 electrons in the form of these bonds that they have. So we can't add them to the hydrogens, which means that the only place we can add those 2 electrons is to nitrogen. Now hydrogens already have the 2 electrons associated with them. They have a complete duet, so that's okay. Let's check nitrogen, whether it has 8 valence electrons. Well, there's 2 from this bond, 2 from that bond, and 2 from that bond. That's 6, 7, 8 valence electrons. Nitrogen is happy. Let's do carbon monoxide, right? These are only 2 atoms, so really the only possible structure is like this or like this. It doesn't really matter. But, they wrote C first, so we're going to write C first. How many valence electrons do we have? 4 from carbon, 6 from oxygen, so 10 valence electrons. But we already have 2 in one of these bonds, so we only have 8 electrons left to distribute. And I'm going to put them on the oxygen first, because why not? Oxygen is more electronegative anyway. So 2, 4, 6, I can't add I can't add anymore. So because oxygen already has 8 with the bond there, so I'll add the 2 more over here. Okay, so oxygen has 2, 4, 6 and a bond to make 8, but carbon only has 2 from the bond and 2 here, so that's 4. So carbon needs 4 more. So what if carbon borrows these 2 and these 2 and they're shared, right? So then what would happen is these 2 become a bond, these 2 become a bond, and so carbon now has 2, 4, 6 from the bonds and 2 over here, 8. Oxygen has 2, 4, 6 from the bonds and 2 over here, 8. Everybody's happy. So there you have it. For carbon monoxide, it's actually a triple bond between the carbon and the oxygen. Whereas for carbon dioxide, it's actually a double bond. All right, let's look at this one. The skeletal structure, we talked about how we put hydrogens at the terminal positions. So and how we put oxygen in a terminal position. So let's draw that. 2 hydrogens, 1 carbon, 1 oxygen. That's our skeletal structure. Let's count valence electrons. 1 from each of the hydrogens, so that's 2, 4 from the carbon, and then 6 from the oxygen, so that's 12. But we already have 2, 4, 6 in the bonds, so we have 6 electrons left. All right, we have 6 electrons left. Where do we put them? Let's start with oxygen because it's the most electronegative thing here, so probably want more of the electrons as possible. 2, 4, 6. That's all of our 6 electrons. And now oxygen has an octet, so it's happy. Hydrogens are happy, they have a single bond, they can fit nothing else. Carbon, not happy, it only has 6 electrons, so it's like, hey oxygen, lend me those 2. So oxygen is like, sure, lends it those 2, and we have a double bond. Carbon now has 4 bonds, each of 2 electrons, has 8 electrons in its valence orbital. Let's look at this guy. We talked about how hydrogens will be in a terminal position, so hydrogens in the end position. That's my skeletal structure. Usually when they write it like this, it kind of gives you a clue as to how to draw it as well, right? So there's 2 H's. These are my 2 H's. There's a carbon, so there's my carbon. There's another carbon to that, and then there's another 2H. So it kind of gives me a clue of how to set up the skeletal structure. All right, valence electrons. There's 4 hydrogens, each with 1, so that's 4 electrons. There's 2 carbons, each with 4, so that's another 8. So that's 12 valence electrons. But we have 1, 2, 3, 4, 5 bonds, each with 2 electrons. So that's 10 electrons, so we need to distribute 2 more electrons. All right, so here's the problem. There's 2 carbons. The hydrogens are already happy. They have a bond. They don't need anything else. Where should I put the 2 electrons? On the left carbon or on the right carbon? Really, it doesn't matter because you'll figure out that they will distribute themselves again anyway. So the left carbon is now happy with 8 electrons. The right carbon is not. So the right carbon is like, hey, lend me those 2. So the left carbon is like, yeah, I'll lend you those 2. So that becomes a double bond. If you want to count all the valence electrons, now you have 1, 2, 3, 4, 5, 6 bonds. 6 times 2 is 12 electrons, which is 12 valence electrons that we needed. There's no lone pairs in this setup, right? No dots anywhere. Let's look at this structure now, HCCH. So HCCH. All right, we have 2 valence electrons from the hydrogens, and from each carbon we have 4, and there's 2 carbons, so that's 8. So we need 10 valence electrons, but we already have 1, 2, 3 bonds, so that's 6 electrons. So if we subtract 6 from 10, we have 4 electrons left. Where to put them? Well, carbons are equally electronegative, so I'm just going to be fair and give 2 each to the 2 carbons, because why not? I'm being generous. I'll share it equally. But neither of these carbons are happy. The one on the left only has 6 valence electrons, 4 from the bonds and 2 from the lone pair. The one on the right, same thing, 4 from the bonds, 2 from the lone pair. So what they're going to do is he's going to share that amount, those electrons, with the one on the right. The one on the left is still not happy, right, because it only has 6 still. But the one on the right is happy now. It's like, all right, thanks for sharing your electrons. But since the one on the left is not happy, it will ask for these 2 electrons to form a bond there. And so in this situation, we have a carbon-carbon triple bond. All right, so I hope that was all making sense. We talked about how do we draw Lewis structures for covalently bonded molecules. We talked about how we form a bond by sharing 1 pair of electrons. So every bond, every line that we draw is 2 electrons. And then we talked about how the reason why they share them is because everything wants to either have a full octet for most of the elements that we're going to work with, or in the case of hydrogen or helium, they want to fill duet because they can only fit 2 electrons. And so everything, whenever we're drawing these dots, we're going to draw lines, or we're going to share electrons and increase the number of bonds until everybody's happy. So the steps to doing that is we draw a skeletal structure first. We then count the number of valence electrons. Then we distribute those electrons. And then if anything is still missing electrons, we just start to share them. to form more bonds. All right, that will bring us to the end of this lecture. In the next video, we're going to talk about situations where that octet rule that we talked about, where things want to have 8 electrons, starts to break down. I'll see you in the next video. Bye.